Okay, this is topic 2 in Unit 4, and we're going to be talking about chemical equations and more specifically net ionic equations. So we have a shorthand method. Hopefully we all took Chemistry 1. We're just going to write down the equation that it gives us in words with its chemical symbol. We're going to add state symbols in AP Chemistry, and we're just going to balance. There's a few different ways to balance. I'll show you my personal way that I like to do it. But yeah, it says it's somewhat imprecise and a lot of trial and error, so you need to make sure that you check them for sure. So first, I have these written. They weren't too difficult, so let's just practice one. So we have magnesium, which is Mg, and that's going to be, let's just say aqueous. We'll assume that it's all aqueous. So 2 positive plus sulfuric acid, which is H2SO4. This is one of the acids you need to memorize, but not quite yet. Acids are always AQ as their state symbol. Then we have hydrogen, which is in its natural state a gas, and it's diatomic, so we need to make sure we have 2. And then plus MgSO4, because we say we have a sulfate, which is just without the hydrogen. Okay, and so this one is balanced. Just to make sure we have our state symbols. There might be a solid, I don't know, I just put some. We have 1 magnesium on the reactant side, 1 magnesium on the product side, 2 hydrogens here, 2 hydrogens here, and then we treat this sulfate as its own little guy. Sorry, usually we put parentheses over it, but I kind of drew the state symbol too close. So yeah, we put parentheses and treat him as its own little ion, and that's going to be 1 and 1, so we're good with that. Let's practice this combustion reaction, number F, real quick. I wrote this little note. We need to feel extremely comfortable with balancing every reaction, but especially for combustion reactions, because we do a whole topic on combustion analysis, and it's a big part of the AP exam. So we have C4H8 plus O2 yields some amount of CO2 and H2O. Remember, in combustion reactions, CO2 and H2O are always our products. So what I like to do is, I like to write a reactant and product chart. So we have carbon, hydrogen, and oxygen. So we have 4 carbons on the reactant side. We have 8 hydrogens on the reactant side, and we have 2 oxygens on the reactant side. And then for the product side, we have 1 carbon. We have 1, 2, 3 oxygens, because we have 2 in the CO2 and 1 in the water. And then we have 2 hydrogens. And what I like to always start off with in these combustion reactions is start with the carbon. So we have 4 here, and so we're going to put a 4 next to here, and that changes our oxygen amount to 8 plus 1 still, which is 9. Make sure we notate that. And then now we need to do the hydrogen, because we always leave the lone elemental element, or reactant for last. So we're going to have, this is a pretty nice one. We have 8 hydrogens on this side and 2 hydrogens on this side, so we're going to use another 4. And then we're going to do 8 here, and now we have 4 times 2 is 8 oxygens plus 4, so that's 12 oxygens. And then since we have 2, the multiple is going to be 6 there. So we have 6 there. And sometimes we are going to have to use decimals, like a 5.5 or like a 6.5, and multiply the whole thing by 2. If you don't feel comfortable with combustion reactions, definitely DM me and I can give you some practice problems, because it's really important to learn how to do. So then we have reactions in aqueous solutions. This is denoted with this state symbol not QA, AQ. Okay. So many reactions are carried out in aqueous solutions, and that's when they're dissolved in water, H2O, before they react. Water is our universal solvent, which means it's pretty convenient and cheap, as long as we make sure it's deionized and there's not a lot of extra bits and electrolytes in the solution. So to do this, we must consider some aspects of how chemicals behave in a solution. And so here we have an ionic compound, sodium chloride, table salt. And remember, these are stacked in a lattice. And so we're going to have a sodium on top of a chloride, on top of a chloride, on top of sodium, and that in three-dimensional lattice, almost like a cube, is how it's drawn. So when the water hydrates these, which means the water attaches to these respective ions, due to the intermolecular forces, these are going to break apart. They're called ion-dipole interactions, and we're going to have basically a hydrated salt. So we're going to have sodium is completely surrounded by water, and chloride is completely surrounded by water, and the negative and positive ends of the dipole are going to be attracted to the respective ions. So for instance, the chloride, we're going to have the hydrogen pointed to the chloride because that's where the positive dipole is. So let's look at electrolytes and non-electrolytes and weak electrolytes. So ionic solutions can be identified by their ability to conduct electricity because they break into ions which carry negative and positive charges. So if there's a large amount of ions in a solution, then the solution will be an excellent conductor of electricity. If you think about Gatorade here, I kind of think about Gatorade. We drink Gatorade to stay hydrated, but it also carries electrical charges with those ions, and so we have a greater response time, and we're quicker, we have more agility when we're playing sports or anything physical like that. It gives our body an excellent boost and carries hydration. So all soluble ionic compounds are strong electrolytes. So any ionic compound that can dissolve in water, so for example, sodium chloride is a great electrolyte, MgCl2, so magnesium chloride is a great electrolyte, calcium, anything like that. Basically all our metals bonded with our nonmetals are great electrolytes. And all strong acid and bases are strong electrolytes. But if it only conducts weakly and so example, a weak acid or a base, it doesn't fully ionize, it's partially ionized, so that means there's some reactant left and it doesn't fully go to product. So we denote that with a two-way arrow that kind of looks like this. And that shows a reversible reaction. So non-electrolytes have no ions present in the solution, so most molecular compounds are non-electrolytes or weak electrolytes. So things like CH4 or C2H5OH, which we'll look at soon. So strong electrolytes will completely dissociate into ions, so we use the one-way arrow, and the strontium ions will be attracted to the negative dipole, so that's kind of what I was talking about in the last example. We have this oxygen with its lone pairs. This is a negative dipole, that's how we denote it here, and this positive ion is attracted to this side, and that's pretty much all we need to know for right now, since we haven't talked about intermolecular forces quite yet. So then we have this reversible arrow, so we have this weak acid, I think this ethanoic acid, yeah. So it'll split into the two ions shown, but not fully. So there may be some rejoining of the ions back into the original compound, and this is how we show this reversible arrow or this equilibrium arrow. So ionic equations. This is a weak electrolyte or a non-electrolyte, so we are not going to have any ionization. It's not going to be soluble in water. Would be the correct way to say it. And so then we have our net ionic equations. So this is only when we show the species that are involved in the reaction. So from here we see this is the net ionic equation. So we have silver plus bromide yields silver bromide. But we see that, okay, well, we only have two species that are actually reacting, that are actually doing anything. So we're going to take out this nitrate and this potassium ion, and on both sides these are going to cancel out, and so we can see that and it yields a solid, which is called a precipitation reaction. That means this is not soluble in water. It joins at the bottom of the beaker or whatever as a powder or a dust or whatever. So we get to some solubility rules. This is the only thing that you need to memorize on the AP exam for solubility rules. We have nitrates. If you don't know your polyatomics yet, we have NO3 negative. Then we have ammonium, not ammonia, which is a different compound. So we have NH4 plus, which is aqueous. And then we have potassium, which is K positive, aqueous. And then we also have sodium, which is Na positive. And this, I denote this NAPS. We denote this NAPS. So NAPS is for nitrate, A is for ammonium, P is for potassium, and S is for sodium. So note that it starts with not the chemical symbol, but it starts with the actual name, and the species above will always be considered soluble. What the heck? So let's just practice one real quick, and we can get out of here. Oh, shoot. Oh no, I'm trying to erase it. I don't want to spoil it. Okay, I don't think I finished this one anyway. So a solution of barium chloride and ammonium sulfate. So barium chloride is Ba. Barium's in the second column of the periodic table, so we have Cl2 because chloride has a charge of +1. And then ammonium sulfate, which is NH4 plus, going times that by 2 because sulfate carries a -2 charge. And then this is going to be aqueous. Oh my gosh, I keep doing Q&A. And then that yields, and we can predict our products because we know our double replacement reaction. They're just going to switch partners. And so we have BaSO4, and those charges are balanced. BaSO4. That's going to be our solid that forms because we know that both of these are not soluble. And then we have NH4Cl. And we can balance this. We can say this is 2 here, and then we're good to go. And then let's just write the net ionic. So this is our species that are involved in this reaction, and we just separate them into ions, and we leave out the spectator ions. So Ba2 positive, aqueous, plus SO4. Make sure you show the charges. Aqueous yields BaSO4. I'm just going to put solid because we know that they're not our NAP, so we assume that they don't dissolve in solution, and that is our answer for that. Keep continuing to practice these, and let me know if you have any questions.